Hello? Okay, so good morning, everyone. Let's start our lecture today. So at the beginning, I want to announce two things. So firstly, our courses will be paused for 2 weeks, okay? In the following 2 weeks. So the point is that because we are going to finish the concurrent programming this week, okay? And we've cut down the lab sessions from 2 hours to 1 hour compared with the previous previous years. So I think most of you haven't have time to get familiar with the content till now, okay? Because we don't have enough time for the lab sessions. So for the next 2 weeks, I will give you some time to consolidate your knowledge in this first part, this concurrent programming, okay? And I will give you assignments to do in the following 2 weeks. And the lectures and labs will be postponed to the end of this semester. So in that way, we'll have more time to work on the network programming and also on your project, okay? So 因为那个就是第一个事情是那个我们下2周的那个课会暂停一下，然后我们会把这个课调到那个学期末。因为我们今天就会把那个并发式编程讲完了，然后但是因为我们的 lab 这个学期被砍到了1个小时，原本是2个小时的，所以我们 lab 基本上没讲什么非常多的内容，然后有很多内容没有时间讲，所以我接下去2周会给你们一些那个作业，然后你们可以根据这些作业呢再去巩固一下前几周学的知识。然后那个下2周的那个 lecture 和 lab 会被移到那个学期末，因为我们那个 networking programming 的那个课时肯定那个 lab 肯定也是时间不太够的，所以就把这2个 lab 移到后面去。然后而且我们那个最后要做那个 project 嘛，所以这样我们就会有更多时间给你做 project。OK。And the next thing is that probably tomorrow will be a typhoon. I think so. So, for students from 362, we will not have lab tomorrow, okay? So we will have an online session today. For the time, I will give you time. I will give you time soon. Okay, today. Okay, so let's start our content today. Today we are going to talk about the last part of concurrent programming. Okay, so it's the first thing is about the deadlock, and then we're also going to talk about some high-level concurrent facilities that you might use during your programming. Okay, so actually the deadlock we've talked a bit in the previous lecture. So this time we are going to talk about more details about the deadlock. Okay, and we are going to give you some example, a very classical example of dining philosophers problem. Okay, and after that, we are going to talk about some high-level facilities like resource pooling, and it will include thread pools and processes pools. Okay, and after that, we are going to talk about some shared variables and shared memory, and also synchronized data structure. It's a kind of new data structure that make your coding more convenient when you're using logs or semaphores. Okay. So let's first talk about deadlock. Okay, so if you still remember that we've talked during the last lecture, I've given you a figure of 4 cars meeting in the cross of a street, of a road. Okay, so it's like they block each other. So if we have this time, we take example of 2 ways single lane. Okay, for example, we have 2 threads or 2 processes, and then they meet in the 2-way single lane. So the left car, the yellow one, want to go right, and the right one want to go left. So they block each other. So now they can move because they don't want to give the way to each other. Okay. And if we write it in 3 processes and 3 resources, we will have a diagram like this. Okay. We have a diagram like this. So it will be like we have 3 processes, process 1, process 2, and process 3. And also we have 3 resources correspondingly. Okay. So the resource 1 is held by process 1. And the process 1 is requesting resource 3. However, this resource 3 is already held by process 3. And process 3 is requesting resources 2. And in the same way, resources 2 is held by process 2. Okay, so we can see it formed up a circle. Okay, and this is called a deadlock. So in this way, none of the processes will be able to get the will be able to get the resources they required. Okay. So if we look at this loop, we'll see there are 4 necessary conditions. 4 necessary conditions to form up a deadlock. Okay. So, I mean, deadlock is not a good thing in the programming, okay? But here we're talking about how it will be formed up. So the first thing is the mutual exclusion. I think you are already very familiar with it. Okay. This means that one of the resources cannot be accessed concurrently. Okay. Because if we don't have mutual exclusion, then process 1 and process 3, they can access resources 3 together. Okay, they will have a race condition. So they will not be a deadlock because process 1 will not wait for resources 3. It will directly go to resource 3 together with process 3 in a race condition. Okay. So mutual exclusion is the necessary condition to form up a deadlock. Okay. And the second condition is hold and wait. So it means at least one process must be holding some resources and waiting for additional resources. Okay, it means, for example, here, each resources is held by one process. Okay. And then this this process who hold these resources one is also requesting for another process. Also requesting for another resource. Okay. So this is called hold and wait. So this is also the necessary condition. And then the third condition for deadlock is called no preemptions. Okay. No preemptions. So preemption means that the resource will not be interrupted, or the processes will not be interrupted by the system and then give the resources to another process. Okay. So it means when resource 3 is held by process 3, the system is not able to interrupt process 3 and give the resource 3 to process 1. This is called no preemptions. Okay, and the last one is a circular wait. The last condition is called a circular wait. So you can see we formed up a circular chain here, right? So if there's a chain, then there might be a risk of deadlock. And if you don't have any chain, any circular chain in your program, then there will not be a deadlock. Okay. So now we know the reasons, obviously the conditions of a deadlock. Then correspondingly, we'll be able to understand how to prevent a deadlock. Okay. So we have 4 necessary conditions. We just need to prevent these 4 conditions. Okay. So we just need to invalidate the deadlock conditions. So, but we know that for the first 2 conditions, actually we don't have anything to do on it. Because we said to prevent race condition between different processes or threads, we must have mutual exclusion. So we cannot cancel this mutual exclusion. Okay. And for preemption, we can also not do anything on it, because this is defined by the system. Okay. So we usually have a preempted system. So the system is not going to interrupt any processes. So it means we cannot do anything on these 2 points. So we can only find solutions in the second condition and the last condition, which is hold and wait and circular wait. Okay, so these 2. So we will try to find some solutions in these 2 points. So usually for hold and wait, we have 2 solutions. Okay, so the 2 solutions is written here. The first one is a process should request all required resources before it's executed. And if it cannot require all the resources it needed, then it just release all the held resources. Okay, so for example, here, process 1 already hold this resources 1, and it is requesting resource 3. However, it is not able to get resource 3. So the solution is just it give up resource 1. Okay, so this is what the first solution do. Okay, and the second solution is that a process requests resources. If a process requests resources incrementally, it must first release all currently held resources and then try to get or re-get them of the new resources. Okay. So because sometimes process 1 will hold resource 1, and then at some time of the program, the process 1 might needs some more resources. Okay, and for example here, if the process 1 is firstly doing something with resources 1, and then after some time, the process 1 needs the help of resources 3. But this resource 3 is already held by another processes. Then what the process 1 will do is that it will just release all the previous resource it hold, and then try to get all the resources it need for the next step together. Okay, so this is the second solution for hold and wait. And then for circular wait, our solution is usually to number the resources and acquire resources in order of the numbering. Okay, so we will give each resource a number. For example, resource 1, resource 2, resource 3, and also a number of each process. Okay, then each process will try to access each resources in an order, in a defined order. Okay, but in this way, there will be some problems. So firstly, to design an effective order for the resources, it's not very easy. Okay, because sometimes you have a very complete program. It will not be like this. Okay, that we only have 3 processes and 3 resources. Sometimes the program will be very complicated. So it will be tough to define an order before it's executed. Okay, and also it is difficult to order dynamic resources. And we need to know a processes. We need to know the resources that are required for processes in advance. But usually it's also very tough to know. Okay, so we usually cannot know very easily that what resources will be held by which processes before we start the program. Okay, so it will be hard to predefine the order and the corresponding relationship. Okay, and also if we are doing the things in a defined order, then there will be a low usage of resources. Okay, because if we do everything in order, then it is not concurrent, right? So if we're not doing in a concurrent way, then there will be low usage of resources. It will be less efficient. Okay. So here is an example how we number the resources and order it. Okay. So a typical rule is like this. If a process holds a resource, it goes to the right of the resource and it can only request a resource on its right. So what does it mean? So usually, this is just like how we define this process, the whole process, okay? So if one process or one thread hold one resources, then we define this process on the right side of the resource, okay? So if we have process 1 holding resources 1, so process 1 will be defined on the right side of the resource 1. And then process 1 can only request resource which has a bigger number than resource 1. Okay, it means if process 1 already held resource 1, it can only request resource 2 and resource 3. Okay, and also like for process 3, if process 3 hold resource 2, so process 3 is on the right side of resource 2. And then process 3 can only request resources which has a larger number than resources 2, which is resources 3 or resources 4, okay? But it cannot request resource 1 anymore, okay? This prevents the form up of the circle, okay? Any questions here? Yeah. Okay. So, actually, I think you might have some questions like, I mean, you might think about it that, for example, in the deadlock, let's take process 1 as example. Why? So in this time, process 1 is trying to get the access to resource 3. So it is waiting for resource 3 and it is holding resource 1. So why we cannot just give the resource 1 to process 2 and then request resource 3? Okay? Why we cannot do like this? Because the deadlock, I mean, like, because the deadlock is usually formed not because hold and wait, right? So it means we are holding and waiting together. So why we cannot do like we don't hold, we just wait. We give back the resource and then we request. The reason is that usually if you are trying to get 2 resources concurrently in the same time, usually you want to write something from one resources to another resources. Okay? Usually for the deadlock, you want get resources 1 and resource 3 together because you've done something in resources 1 and then you have some data or variables. Okay? And then you want to transfer this data to another resource. Okay? If you give back the resources 1 to process 2, and then process 2 will do something to resources 1, and then all your data, your memory will be changed. Okay, so after you get the request from, I mean, after you get resources 3, the thing, if you haven't held the resource 1 during this time, there will be a risk that the things in resource 1 will be already changed by some other processes. Okay, so that's why we need to hold this resource 1 and then request resource 3. And this is also the reason why deadlock happened. Okay. Yeah. And then, so actually, this is just some concept here. Okay. Deadlock can be detected using a resource allocation graph like this. Okay. This is called a resource allocation graph, also like this one. Okay. So you easily know if there's a deadlock here, if it form up a circle. Okay. So it is a closed directed circle in the graph indicates the deadlock. So usually you have 2 ways to recover this deadlock. Okay, but they are not very good ways. Okay, so the best way is to prevent deadlock. But if a deadlock already there, then we can have 2 ways to recover the system. So one is to terminate the process. Okay, so cue a victim process. So in this circle, okay, because we know that, for example, process resources 1 is held. Resource 1 is held by process 1. That's why process 2 cannot request resource 1. Okay, so we just terminate process 1. Okay, then this resource will be released. So process 2 will be able to get the resource from resource 1, and then it can do a task. So the problem solved. Okay, so this is called process termination. Okay, and resource process preemption is actually similar. Okay, I just like to preempt and to restart from a safe state. Okay, so actually it's very similar. And the problem is like it is not easy and sometimes not proper to select the victim process. Okay, so we don't know, like we have 3 processes here, so which one we need to terminate? It's usually hard to make choice. Okay. Okay, so now you've know the concept of deadlock. Let's talk about some examples. So this is very typical example during programming, which is called dining philosopher problem. Okay. Okay, so let's say we have 5 philosophers. Okay, and they just know they just know about 2 things: think and eat. Okay, like your teachers. Okay, because usually they are PhD, like Doctor of Philosophies. So they just know about thinking and eat, right? And so in order to eat, philosopher will try to get 2 chopsticks. Okay, so let's say they are Chinese. Okay, so they need 2 chopsticks to eat, and they need to get 2 chopsticks. Okay, and they must get 2 chopsticks to eat food. Okay, and if they just get 1 chopsticks, then they will be, I mean, they are very stupid. So they will just hold these chopsticks and wait for another one. Okay. And then after the philosopher have eaten the food, it will put back the chopsticks to the table. So another philosopher will be able to get the get the chopsticks. Okay, maybe the chopsticks a bit dirty, but they don't care. Okay, they share the chopsticks. And in this occasion, you need to write the program for this scenario. Okay, so in one way, you might write the things in like this. Okay, so this might be an incorrect solution. Okay, but this solution is quite intuitive. So, I mean, at the beginning or at the first time when you're trying to write the program, you might write in this way. Okay, so there will be a program of philosopher. Okay, and we know we have 5 philosopher and 5 chopsticks here. Okay, so we have ID for each philosopher. P0, P1, P2, P3, P4. And also we have ID for chopsticks. C0, C1, C2, C3, C4. Okay, so for each philosopher, it will start the loop first. Okay, it will think first. Okay, after think, okay, maybe, yeah, after think, he will wait. Okay, because after he think about something, maybe why his wife is angry on him last night, so he will start to eat. Okay, but before he eat, he need to acquire the chopsticks. Okay, so he need to wait for the chopsticks. So what means wait? What means wait? Okay, wait means acquire, right? We've talked about it in the previous lecture. Wait means require. So here it is going to require chopsticks. And let's see let's make a rule, okay? So all these philosopher will request or will try to acquire the chopstick on his right side first, and then the one on the left side. Okay, so for P01, for P0, he will try to acquire C0 first and then C1. And also for P1, it will try to acquire C1 first and then C2. The same way, P2 will try to acquire C2 first and then C3. Okay, so this is the rule that we make. So if we write it in this code, then it will be like this. It will try to acquire the chopsticks with his ID number and then the ID number +1, which indicate the left one. Okay, this is the right one, this is the left one. Okay, and then after he gets both chopsticks, it will start to eat. And after he has finished eating, he will signal the chopsticks. So signal here means release. It will release the chopsticks. And then we end the loop. Okay, so what means mode here? What is mode? Mode means to get the remainder. Okay, remainder. So for example, let me see if I can use the no. Tools. Okay, doesn't matter. So let's say, okay, so this mode here is just used to solve the boundary occasion, okay, the boundary condition. So for example, if we for philosophy P4, okay, the ID is 4, right? For this philosopher P4, the ID is 4. So ID 4 plus 1 is 5, okay? And 5 divided 5, the remainder is 0, okay? So then this number becomes 0 again. So which means C0 here, okay? So P4 is trying to get C4, and C4 plus 1 is C0, okay? So this mode here is just to calculate the remainder, okay? And if we have like C3 or C4 divided by 5, the remainder is 4 and 3 itself, okay? This is why we are using this mode operation here, okay? It's just to deal with the boundary occasion, okay? Okay, so this is the program. This is the solution for this problem, okay? So it might be incorrect. So if we write this in the code, it will be like this. We will have a function of philosopher, okay? We will have its ID, and the n value, the times of the loop, and the chopsticks, okay? So the philosopher will try to acquire these chopsticks on his right side first, and then acquire the chopsticks on his left side. And he will eat and then release both chopsticks. Okay, then we will need to define the chopsticks as a semaphore. Okay, so each chopsticks will be one semaphore, indicating the resources. So we will have 5 semaphores and also 5 threads for the philosopher. Okay, and then it will be, if we run the program, it will be like this. If we do this dining for 100 times, if we are lucky, there will be no problem. But if we are not lucky, then there will be a deadlock. Okay, so the deadlock will be like this. P0 is holding this C0. Okay, so it is trying to get another chopsticks to eat, C1. But this C1 is already held by P1. And P1 is requesting C2, while C2 is already held by P2. Okay, then there's a deadlock. Yeah, so what we need to do to prevent this occasion, to prevent this deadlock occasion. So here I'm going to give you 3 examples or 3 solutions to solve this problem, okay? So the first one is also the easiest one, I think. Okay, so we just define that at most, 4 philosophers can eat concurrently. Okay? So we will have another semaphore. So we will have another semaphore. So in total, we will have 6 semaphores. Okay, and this extra semaphore is named as Sam, okay? So this Sam has an initial value of 4, indicating that at most 4 philosophers can eat concurrently. And if you still remember the things from the last lecture, this is very similar with the buffer size, okay? So if we go back to this problem, we can see that if we define that every time only 3 philosophers can eat. So for example, if P0, P0, P1, P2, P3, they are trying to get chopsticks. P4 will just wait. Okay, so then C4 will not be held by P4. So P3 will be able to get C4. So C3 will be able to eat. And after P3 finish eating, P2 will be able to eat. Okay, so we'll do in this way. That's why we define that at most 4 philosophers can eat concurrently. So in this way, we prevent a circle, okay? So we don't have any circular weight in this scenario, okay? So how we write it in code? We can write it in this way. So we wait. We acquire. First, we put an extra line waiting for the semaphore of Sam, okay? And we check if there are already 4 philosophers trying to eat, okay? If there are already 4 philosophers trying to eat, then the 5th philosopher will be blocked here, okay? So the 5th philosopher will not try to get the chopsticks. Okay, so the chopsticks on his left side will not be held by him. Okay, so after one of the philosopher finish his task or finish eating, he release all his chopsticks. And then also we increase the number of Sam by 1. Okay, so then we will have, the rest semaphore, the 5th semaphore will be able to acquire the remaining chopsticks. Okay, so this is one way. So if we write it in the code, it will be like this. We just need to add one more line. We just need to define one more one more semaphore with a number of 4. So this 4 represents the maximum thread that can access the following code in this philosopher function. Okay, and then we just add one more line here. If there are already 4 threads which have already acquired Sam, then the 5th thread will be blocked here. Okay. Okay, and then let's talk about solution 2. Okay. So in this in this solution 2, we are going to give an order of the chopsticks. Okay. So you might say that we already have order here: C1, C2, C3, C4, C0. But actually, this is not order. Okay, this is a number, but it is not ordered. It's just an index of the. It's just an indicator of the chopsticks. So in this solution 2, we are going to give an order for the chopsticks. Okay, according to the indicator, we are going to order it before we acquire it. So how we order it? Actually very easy. Okay, so every time because the original solution is that we define where's the diagram? We define all the philosopher, they will get the chopsticks on their right side first, and then left side. Okay. So for P4, he will get C0 first, and then try to get C4. And this is also the origin of this deadlock. So what happened if we reorder the chopsticks when it is trying to acquire it? So we reorder it in this way. If the index of these chopsticks, oh, sorry, my fault. Okay, so in the previous solution, that what we've predefined is that P4 will try to get C4 first. Okay, sorry. because he will get the chopsticks on his right side first. So P4 will get C4 first, and then it will get C0, okay? So the order is C4 first and then C0. So if we reorder it, that if P4 will try to get C0 first and then C4, we also solve the problem, okay? Okay, then we do in this way. So we firstly check the number of the chopsticks. If ID, this means the one on the right side, okay? Yeah, if the right side chopstick is smaller, the number of right side chopsticks is smaller than the left side, then we don't change the order. However, if the right side chopsticks is bigger, the number is bigger than the left side. So especially the occasion here, C4 and C0, the right side is bigger than the left side of P4, okay? Then we reorder it. We will get C0 first, okay? So it's like this. Yeah, it's like this. Else, ID1, ID2 is equal to ID1 plus 1 and then ID. So it's like we reorder. We put ID plus 1 first and then ID. Okay? So then we solve the problem. Why? So for P4, previously P4 will try to get C4 first. And so C4 might already be held by P4 when P3 is trying to request C4. Okay? But if this time P4 will try to get C0 first, and if C0 is already held by P0, it will not do anything, okay? It will not hold C4, okay? So then P3 will be able to get C4 and C3 together. So P3 will be able to eat, and then everything will work, okay? So this is how we do it to define the order to solve this deadlock by defining the order of the resources. Okay, so this is the, if we go back to see the things that we've done before, is here. Number the resources and acquire resources in the order of numbering, okay? And then let's talk about solution 3. Okay, actually solution 3 is very similar with solution 1. So solution 3 is like we define one more semaphore, okay? And this semaphore has an initial value of 1. Okay, but this semaphore is used to check if one philosopher gets 2 chopsticks together. Okay, so if doesn't, then it will be blocked. Okay, it will be blocked here. So for example, if one of the philosopher already get, oh sorry, my fault. So this semaphore is used to define that every time only one philosopher can try to acquire 2 chopsticks. Okay, so if one of the philosopher already tried to get 1 chopsticks, okay, then this semaphore S, the value will be 0. So other semaphores will all be blocked on the first line of weight S. Okay, so the first philosopher will be able to get 2 chopsticks together, and then after it get the two chopsticks together, it release S, okay? Then the other philosopher will be able to access these two lines to get chopsticks. And again, they are each philosopher, when it has the right to get access to one chopsticks, other philosopher will be blocked again. Okay, so it ensures that every time only one philosopher can have the right to access to the chopsticks, and all other semaphores will be blocked. Okay. Then the same thing. After the philosopher eat everything, it just release the chopsticks and end loop. Okay, so this is solution 3. Okay, so this is the first part of the lecture. And any questions about these 3 solutions? If no, then we will have a 10 minutes break. Okay, let's start at maybe 10 o'clock, around 10 o'clock. Okay, so everyone, let's go back to our lecture. And because I think we have more people here now, so I want to talk about the things that I've mentioned at the beginning of this course again, okay? So we are going to pause this course for 2 weeks, okay? So for the following 2 weeks, you don't need to come for the lecture and the labs, okay? The reason is that because we are going to finish this concurrent programming today, okay? So this is the first part of our course. And then next we are going to talk about network programming, okay? So concurrent programming is the first part of this course. But the problem is that we don't really have much time to work on the code, okay? Because the lab session have been cut down from 2 hours to 1 hour this semester. Okay, so quite a lot of the lab coding haven't been done yet. Okay, so I think most of you are still not very familiar with the coding part. So I will give you 2 weeks to consolidate what you've learned from the previous weeks. Okay, and I will give you 2 assignments during these 2 weeks. I think I will combine them together. I'm not sure. I think I will tell you later. Okay. I might give you 2 assignments. I will give you 1 assignment. I will combine the assignments together. Okay. I will give you 1 assignment, and then you can try to do it in these 2 weeks. Okay. To consolidate what you've learned before. Okay. And then these 2 lectures and 2 labs will be postponed to the end of the semester. Okay. So that we will have more time to work on, we will have extra sessions to work on the network programming. So this network programming will be combined together with concurrent programming. So I think it will be more difficult, okay? So that's why we need more time. So we'll postpone this lecture and the labs to the end of the semester. And also you will have more time working on your project, your final project, okay? Okay, so then let's start our lecture today. The second part of the lecture today. So it's about some high-level facilities that you might use during coding. Okay, the first one is the resource pooling. You might already heard about it before, okay? But in this case, we're mainly talk about threads, okay? Resource pooling for threads and processes. So why we need the resource pool? Okay, resource pooling is just like you create some resources. You create some resources in advance, and then when you are going to use it, you just borrow it from the pool, and then after you finish the task, you return it to the pool. Okay, this is called resource pooling. And regarding the threads and the processes, just means that we create some threads and processes and then put them together inside the pool, and then when we need it, we just borrow it from the pool and then return it after the threads and processes finish its separate tasks. Okay, so why we need to do this? So imagine that we don't use resource pooling. Okay, every time we don't have any thread and processes, we need to create one. Okay, and after we create these thread and processes, these threads and processes will try to do application. And after the application is done, it will destroy the threads and the processes, and then no process and the threads existing anymore. Okay. So this creation and destroy of these threads and processes will take a lot of time and the resources. Okay. Especially for processes that we've mentioned before. Okay. Creating processes will take a very long time. Okay. That's why we need to do resource pooling. Okay. So in this way, we will try to create a number of threads and processes before we start the program. And every time when we need to use it, we land from the process. We land the process from the pool. So we don't need to create processes. Okay, so it can save time and resources. So how we manage this kind of resource pooling? So we have like allocation policies and also some other management options. So these allocation policies, we also have 2 kind of allocation. One is called pre-allocation. Okay, so this is what I've already mentioned. So we create a number of resources initially. Very easy to understand, right? Before the program starts, we create a number of resources. And another one is called on-demand allocation. So it means only create a resource only when needed. Okay, so this is very similar with what we've done before. So we don't create we don't create processes in a pre-allocation way. We just create when we need. Okay. But in resource pooling, we usually combine these two together. Okay. So it is usually a combination of pre-allocation and on-demand allocation. So it means we will create a resource pool initially, then we will borrow from it and return it. But sometimes the application might need more, okay? Because it is hard to define how many resources we exactly need, okay? So usually we start with a rough number. And if we don't have enough resources in the middle of the program, then we will use this on-demand allocation. We will create resources when we need more, okay? So it's a combination of pre-allocation and on-demand allocation in resource pooling management. Okay, and also we have some other management options. For example, set a limit on the maximum number of resources allocated. Okay, so this is also sometimes being used. Okay, so when we create this resource pool, we will set a maximum number. Okay, and also we release resources when a lot of resources are idle for a long time. So because sometimes we might create too much resources, we might create too many threads and processes. And then these processes and threads, it is in the resource pool, but it is never used, or it hasn't been used for a long time. So we just release them to save resources. Okay. So these some other management options. Then let's talk about some pros and cons, or we say advantage and drawbacks of resource pooling. Okay, so of course, firstly, it will have a better performance for the system because we reuse the resources. So we avoid repeated creation. We save time and resources. Okay, then we have centralized control of resources because we put all the resources in a resource pool. Okay, so it will be more convenient for us to manage these resources. For example, we might set an upper limit of the resources used in the system. It's kind of centralized control. Okay, we put them together, so we manage them. We manage them together. So also when we put them together and manage them together, then it will be more convenient to interact with the resources. Okay, so it supports more convenient interface to use the resources. You will know about this when we are doing coding later. Okay. Okay, but there are also some small problems. Okay. For example, we might have some overhead to manage the resources in the pool. Okay. Yeah, because we need some extra resources to manage the resource pool. So there'll be some overhead. Okay. And it might have some waste of pre-allocated resources. Okay, this is similar with what we've talked about here. Okay, because sometimes when we predefine too many resources, too many threads or processes, some of them will be idle for a long time. Okay, so it is a kind of waste. Okay, that's why we need to release them. Okay. Yeah. So you can see actually this problem or these drawbacks can also be solved by this manage option here. Okay. But of course it will cause some waste of resources. Okay. Yeah, then let's talk about the coding of the thread pools and also the process pools. And the first one is the thread pool. Actually, the thread pool and the process pool is quite similar, I think, almost the same. Okay, the idea are almost the same. We just need to use different APIs. And these days, we usually use more than APIs here, okay? And this is already discarded. It is already being discarded, okay? So usually we use this one. So we will have a module called concurrent. Okay, then inside this, we have a thread pool executor and process pool executor. Okay, and then we will have a look on the things here. Okay, let's talk about the thread pool executor first. So we can define a max worker. Okay, what is max worker? So this is like the thing we've defined here. Set a limit on the maximum number of resource allocated. Okay, so this number of worker is the max. Sorry, the max worker is the maximum number of thread that we are going to pre-allocate. Okay, then we can also define a name for the thread. Sometimes we also have an initializer. What is initializer? So it means every time when the thread starts, it will do something at the beginning. Okay, you can define something for the threads to do at the beginning. And then also there are some arguments for this initializer. Okay, usually in our coding, we usually don't use this. Okay, we just keep everything empty. Okay, and the default value of maximum worker is the number of CPUs multiplied by 4. I'm sorry, by 5, okay? So if you have like 8 CPUs, 8 core of CPUs, then your maximum worker by default, it will be set to 40, okay? And after we've defined this pool executor, the thread pool, we will have some functions to use the thread, okay? So one is called submit, another is map. We will talk about these two functions later, okay? It's actually very similar. Submit, this is the target function, the arguments of the function, and the key arguments of function. I don't know if you are familiar with key functions. Okay? So sometimes you say like, let's just use this function map as example, okay? Oh, sorry, key arguments, sorry. I don't know if you're familiar with key arguments, okay? But let's talk about, let's take this map as example. So we see there are some arguments for the map, right? So we can say this function is the arguments. Iterables is also arguments. And this one, time out equal to something or trunk size equal to something. This is called key arguments. Okay. So what's the difference with key arguments and arguments? So it has a name for these key arguments. And with these key arguments, you don't need to write in the correct order, okay? You can put this after this, also fine. After trunk size, also fine. Okay, this is called the argument. I think you've learned about it maybe, but it's a revision, okay? And also then let's talk about the idea of this map function, okay? The same thing, it will have a target function for the thread, and then it will have iterables. So this is different with submit, okay? Iterables can be a list or tuple, okay? I will show you some example later. I think you might be a bit confused about this, but later, after you see the example, you will know. Okay, so here is one thread pool example. So we just need to import this thread pool executor from this module, okay? And the same thing, this is our old friend, printing table tennis and movie, okay? Sorry, not table tennis, tennis and movie, sorry. Printing tennis and movie. Okay, this is what we learned like 2 weeks ago, I think. So if we are using thread pool here, we just need to change the code to this one with thread pool executor as executor. Okay, we need to use the with statement. So why we need to use with statement? So if you still remember that in the first lecture when we were talking about use, sorry, when we were talking about the use of with, we see that with will have two steps. It will do these things and then close the things. Okay, so in this case, it will do the things and then give back the executor back to the thread pool. Okay. Okay. So this is why we need to use with the thread pool executor as executor and then use the executor. Okay. Then here we are using this submit method. Okay. So this is very similar like when we are creating the thread separately. We just give a target function and the arguments of the target function, like here. Function and then arguments of the function. Okay. Then end. Okay, very easy, right? So it will have the same output as before. Printing the movie and tennis in an interleaved way, okay, concurrently. Then here is another example use for another one to add, okay? This is also our old friend. Okay, so we want to add two elements to integer together. Okay, and this time we are using map. Okay, executor dot map is this one. This function, map function here. Okay, so what is iterables here? As I said, usually it is a list or tuple, okay? So here, these two lists are iterables, okay? So how we do it? We add the first element of the first list and also the first element of the second list together. So this, because it is an iterator, okay? It will do this thing first and then one by one. Add these two together and then add these two together. So that's why it is called the iterator, okay, iterables. But like, please keep in your mind that it will add the elements from the first list to the second list, but not the first inside the first list, okay? So if we have two lists, the first list is the iterables of A, the arguments A. The second list is the iterables of the arguments B here, okay? So if you have A, B, C, then you can also put another list here after that, okay? So after you print it, it will show you that main process, thread pool executor. Okay, this is the name of the thread, okay? You have 3 threads, and each thread is doing, the first thread is doing add A and B, which is 1 and 10. The second is adding up 2 and 20. The third is adding up 3 and 30. Okay, one by one. But in a concurrent way. Okay, then in the end, if we print the list, then it is 11, 22, 33. Okay. Then one thing here, like this method returns a generator. Okay. This map function method doesn't return the value, but a generator. What does it mean? So if we say we have print 2 times here, the first time when we are using map, okay, so you might think that after we call this map function, we'll directly get the result, but actually not. After we call this function, we get a generator. Okay, so if we print this res here, we didn't get the result. We have things here. It print a generator. It give you the information of the thread and what task it is going to do. But it didn't give you the result of 11, 22, and 33. Okay, only when you are going to use this one. Okay, like you are going to use the like a list. Okay, you use this list function and then put this result inside this list function. Then this generator will start to generate result. Okay, and then you can print the list. And after that, you will see the result. Okay, it means if you directly print the result, you will not get the final result. It will just return a generator. Okay, so this rest here is a generator, not the result. So I've also mentioned here, okay? So the math function returns a generator, and the generator is a type of iterator, okay? So if you're using with like a list or some other functions, it will give you the result, okay? So if you want to print it one by one, then you need to use a for loop, okay? And then print this one, the result that you get, okay? You need to use a for loop to print it. So the easiest way is that you use a list, okay? Or you directly use some other function to do some other operations. It's also fine. Okay, then this is about process pool. Process pool. Actually, it's very similar with the thread pool, okay? The function are almost the same, but you are just using another method called process pool executor. And then also we are using this tennis and movie example, okay? And then what's the difference here? You can see the result. Here it tells you that it's fork process, or this is just like a name, okay? It's for different systems, it might have different name, okay? You see process 1, main thread. Process 2, main thread. Process 3, main thread, okay? So it means for each process you create, it has a main thread. And then it is doing this, add them together. But if we look back for the thread pool, okay, you will see they are in the same main process, okay? Main process, main process, main process. They are the same process. And in the main process, it has 3 different threads, okay? Thread 1, 2, 0, 2, 1, okay? Oh, sorry, 0, 1, 2. Okay, so this is like, as we said, thread is sharing the resources in a single process, okay? But when you're creating a different process here, in each process, it will only use one thread. Okay, then here are some other examples that you can have a look, okay? I'm not going to talk about the details because all these examples we've talked before. And here we just use some different ways. We just use these thread pools to run these things again. Okay, so I think there are nothing important. Okay, but yeah, there's one thing that I want to mention here. So previously we see that we divide this adding up from 0 to 1 million to 2 tasks. One is from 0 to 500,000 and 500,000 to 1 million, right? So if we split to this pool executor, process pool executor, we use this map function. We can see the argument is from 0 to half and half to n, right? So here you need to pay attention. When we are doing this operation, we are adding from 0 to this. We are adding from this one to this one, okay? The first element in this list and then the first element in the second list. We are not adding from here to here. Okay, so if there are sometimes the number from here to here is different, you should know that we are doing from 0 to half here, and then half here to the n. Okay, so it's adding up correspondingly. And also the code here are the same as before. We just change some process pool. Okay. Then let's talk about shared variables and memories. So actually, we've also mentioned it before. We know that thread, they're inside one process. Okay, thread 1, thread 2, they're inside one single process. So thread 1 and thread 2, they can access to the same variable easily because the variable is shared in both thread 1 and thread 2. But if we are using multiprocessing, okay, then we might have the same name variables in two different processes. And in this time, if we change the variable, even the name is the same in process 1, there'll be no difference. It will not make a difference to process 2. Okay? So the variable in another process will not be changed. So that's why for communication or passing data between processes, we need to use a shared memory. Okay, and this is a system level facility. Okay, so this shared memory can be simultaneously accessed by different processes. So they can, after process 1 doing something, and after process 2 doing something, they can share their results in this shared memory space and then get some other result or other data we need, okay? So then we need to use some synchronized data structure. So let's talk about thread again first. Oh, sorry, this is not for thread. This is only for, yeah. Oh yeah, also for thread. Oh yeah, thread can also use it. Okay, but they are from different modules. Yeah. Okay, so let's talk about thread first. So we have a class Q, okay, and then in this class Q we have a method Q. Sorry, in this model Q we have a class Q, which is a method. Okay, and then in this in this class Q we have several other methods to deal with the data inside this queue. Okay, let's go ahead to the code together directly, okay? So previously, we've talked about this producer and consumer example. And if you still remember that we need to create 3 different semaphores. One is used as log. Another 2 is used to check the size and if the buffer is empty or not, okay? So it's quite troublesome, right? But doesn't matter. In this Python library, it provides you some other data structure, which is called this queue, okay? So we can see like, if we use this queue, dot put, we write data to the buffer. And then internally in this queue dot put, it already has the semaphores for log and also to check the buffer size and if the buffer is empty or not. So there's already code written in this library. That's why you don't need to define by yourself anymore. Okay, you don't need to define your own semaphores separately. Okay, you can directly use this q.put data. Okay, and correspondingly, you also have q.get for this consumer to get data from the buffer. Okay, so we replace the previous 4 lines, I think, by this one single line. Okay, so it is more convenient. But of course, it will not be that flexible as before, that you cannot customize the things by yourself. But it is more convenient for you to do coding for this producer and consumer example. Okay. So this is some kind of data structure to facilitate your coding. Okay. Yeah. So if you run the result, it will be the same as before. Okay. There'll be no problem if you set the maximum buffer size at 3. So, but you need to pay attention that when you're defining this queue, you need to put buffer size inside, okay? Then the queue will know what's the buffer size it need to check. So if you set the buffer size at 3, it will not exceed the length of 3. Okay, then there's another queue for processes, okay? But it's a bit different. It is inside this module of multiprocessing. Because we know that for thread, they shared the memory space inside the process, okay? So that we can directly use the Q, but for processes, they have separate memories. Okay, that's why we need to create a shared memory, okay? And we need to use this multiprocessing module to create this Q, okay? Let's also have a look on the example code. Okay, so we will do like this. Q equal to multiprocessing.q buffer size. Actually, it's very similar, right? So for the thread, it's like Q is equal to Q directly. And then in this multiprocess one, we need to use this multiprocessing module. And then the method inside this multiprocessing module to define this Q. To define this Q in a shared memory, okay? Also, we put the buffer size inside. And all other things are quite the same. Then we just like put data inside the Q and then get data from the Q, okay? So Q is usually used for buffer. And also, you may ask, what about like single value, okay? Then we have another function called value, okay? Yeah. So how we use this value? I think I haven't gave you example here, but here it is like this. We just write like value equal to 5, okay? So for Q, we usually use this put, right? But for value, because we just need to write a single value, so we just put the, for example, an integer, give the number, give the value to the value. And this is the class. This is the method, okay? This is the name of the class that you initiate, instantiate, okay? And this is the method. This is the function inside this class that you can use, okay? And this is value.value equal to 5. You write 5 to the value of this value class that you defined. Okay, but the problem here is that q.put 5, this is a atomic method. And also, for example, this one, value equal to 5 is also an atomic method. It's just one step. And sometimes we have a statement look like atomic, but actually not atomic. For example, when we're using value.value is equal to value plus 20. It just looks like one line, but actually there are 3 steps. So firstly, we'll get the data from value.value, and then we will add the data by 20, and then we rewrite this data back to the value, okay? So actually there are 3 steps. So if there are 3 steps, there might be a race condition, okay? So how we deal with it? Again, we need to use a lock. So very simple. For this data structure, it already provides you the lock method inside. So you just need to use with get lock, and then use this line again, okay? Then it will be atomic, similar as this one. If you write in this way, they are the same, okay? So then you prevent the things from a race condition. Okay, so any questions here? Okay, if no, then it's the end of this class. And yeah, so we will have a lab session later for students from 4620. And other students, you can just leave. Thank you very much, and see you 2 weeks later. Yeah. And if you haven't taken attendance, you can take attendance here. And if you have any questions, please let me know before we end up the class, okay?